Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you for joining me here today as we begin our second video in our series on scientific notation. In our previous video, we talked about the fact that scientific notation is a special way of writing numbers that allows us to write very, very large or very, very small numbers in a way that makes them easier to work with. And we said that the number is written so that it is the product of a number between 1 and 10 and 10 raised to a certain exponent or power. And then I gave that to you in fancy math terms. We have this constant factor over here multiplied by a bunch of 10s to turn it into the form we want. And we said the rule is that this constant number or this factor at the beginning has to be a number between 1 and 10. Now we are going to review that just very, very quickly to make sure we're all on the same page. But then today we're going to talk about how we can compare and order numbers when they are written in scientific notation. So let's take a look at this. A boulder in Colorado weighs 52,000 pounds. Write this in scientific notation. In standard form, 52,000 looks like this. This is how we are used to seeing it. But we know that we can write this as 5.2 times 10,000 because in our previous lesson we said that every time we multiply a number by 10, our decimal point is going to move. So in the case of 5.2 times 10,000, this decimal goes from being between the 5 and the 2. It goes 1, 2, 3, 4 places. 1, 2, 3, 4 zeros to make it into a 52,000. So in scientific notation, we would say that this is 5.2 times 4 tens, or times 10 to the fourth power. Remember, 10 to the fourth power is the same as 10,000, and this 4 indicates for me how many places this decimal will move. If that's confusing, you're going to want to go back and re-watch our previous video on scientific notation to help that make more sense. Likewise, if I were to give you a really small number like 0.00003 or tenths, hundredths, thousandths, 10,000ths, 300,000ths, notice this is a very, very tiny number. I can take this 300,000ths and I could write it as 3 times 100,000 or 1/100,000th if I wanted to put it in fraction form. And I happen to know that 100,000, since it has 1, 2, 3, 4, 5 zeros in it, is the same as 10 to the fifth. And I happen to know that 1 over 10 to the fifth from my exponents unit is 3 times 10 to the negative fifth. 1 over 10 to the fifth is the same as 10 to the negative fifth power. Notice once again, if my decimal is here after the 3 and I have a -5, that says I'm going to move that decimal 5 places in the direction that makes that 3 smaller. Or if you think of it up here as being 3 with a decimal, I'm going to move that decimal 1, 2, 3, 4, 5 places. Hopefully that makes sense. If you're uncomfortable with that, again, go back and watch our expanded explanation of that in our scientific notation video. Our focus for today is on problems like this. The temperature on Mercury is roughly about 7 times 10 to the first degrees. The temperature on Neptune is about -3.92 times 10 to the second degrees. Use greater than or less than or equal to compare these temperatures, and how do you know? So in this problem, I'm given 2 planets, and I'm given their temperatures written in scientific notation. And I'm asked to determine whether Mercury's temperature is greater than, less than, or equal to Neptune's temperature. Some people get overwhelmed by the fact that these are in scientific notation, but there are some pretty easy strategies that you can use in order to solve this problem. In fact, we're going to develop 3 strategies today, and then we're going to tie all those together at the end to help us with putting numbers in order when they're written in scientific notation. To help us with this, I am going to go ahead and put these into standard form. 7 times 10 to the first says take the decimal, which should be located right here, and move it 1 space to the right. That's going to give me 70. And then over here, -3.92 times 10 to the second. This 10 to the second says to take this decimal and move it 2 spaces to the right, giving me -392. Now that those are in standard form, it should be relatively easy for you to tell which one is larger. Of course, a positive 70 is going to be greater than a negative 392. So the temperature on Mercury is greater than the temperature on Neptune. I picked this example because it illustrates very easily for us a very important strategy, and that is positive numbers are always greater than negative numbers. Positive numbers are always greater than negative numbers. In a situation like this where we have a positive 7 over here and a negative 3 over here, it really doesn't matter what my exponent on the 10 is, because no matter how many 10s I multiply this by, and no matter how many 10s I multiply this by, this is always going to be a positive number. And a positive number will always be greater than this is a negative number. A positive number is always greater than a negative number. So if I were to give you another example that looked like this, you could probably pause the video and very quickly try that on your own, but hopefully it's not overwhelming for you, because what's happening here with the exponents really doesn't matter in determining which one is larger, because I can clearly see that this is going to be a negative number and this is going to be a positive number. A negative number is always less than a positive number, regardless of how many zeros it has on it or how tiny a decimal it will be. If you wanted to see this in standard form, again, this is 51 tenths, hundredths, thousandths, 51 ten thousandths, and it is negative, so it's below zero. This is tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. This is 24 10 millionths. This is a much tinier number, but it is above zero. This is a number that is farther from zero, but it is in a negative direction. This is strategy number one. Positive numbers are always greater than negative ones. Here's another problem for you. The sun has a surface temperature of approximately 1 times 10 to the 7th degrees. An atomic bomb has a temperature that can reach as high as 1.5 times 10 to the 8 degrees. Use greater than, less than, or equal to compare these temperatures, and how do you know? So we have the sun, there it is, and it has a temperature of 1 times 10 to the 7th. We have an atomic bomb that has a temperature of 1.5 times 10 to the 8th, and we are asked to compare those. Can you do that without me showing a strategy? Maybe you want to pause the video and take a moment to think about that. Here's what I'm going to do. I'm going to go ahead and write this out into standard form for you. 1 times 10 to the 7th says take that decimal after the 1 and move it 1, 2, 3, 4, 5, 6, 7 places. Over here, 1.5 times 10 to the 8th says take that decimal from between the 1 and 5 and move it 1, 2, 3, 4, 5, 6, 7, 8 places. When these are in standard form, hopefully it's very easy for you to see which is larger. 10 million is smaller than 150 million. 10 million is smaller than 150 million. And you can see it clearly in standard form. The question is, how can I know that without having to bother putting it in standard form? When I look over here, this has a 1 and this has a 1. But it's important for us to realize that when we start multiplying by tens, the place value of this 1 changes. It's not a 1 in the ones place, it's actually a 1 in the 10 millions place. This one right over here is worth a whole lot more than this one, because this one is in the 100 millionths place. This one has a value that is 10 times greater than this one. How do I know this has a value that's 10 times greater than this one? Because this one is pushed over 7 spaces, or this one's going to have 7 zeros after it. This one gets pushed over 8. And that leads us to strategy number 2. The bigger the exponent is, the bigger the value of the number. Bigger exponents make bigger numbers. So when I look at these and I realize they are both positive numbers, I can look over here to the exponent second and I can say, well, this is only going to go out 7 spaces. This one is going to have a place value that increases by 8. Therefore, this one is the larger number. Strategy number 2, bigger exponents make for bigger numbers. So when I give you something that looks like this, 3.7 times 10 to the negative third, the first thing so when I give you this problem, 3.7 times 10 to the negative third and 8.1 times 10 to the negative fifth, and I ask you which of those is the larger number. Is this greater than or less than or equal to the one on the right? The first thing I always check for is, are they both positive? And these are. Remember, strategy number one said if one of them was negative, that would have made this really easy. But when I go to compare these, they're both positive, so I move on to strategy 2. Bigger exponents make bigger numbers. The exponent on the left is a negative 3. The exponent over here on the right is a negative 5. Which of those exponents is larger? Well, negative 3 is larger than negative 5. Therefore, when I put them into standard form, you're going to see that this 3 is 3 hundredths, but this 8 is 8 tenths, hundredths, thousandths, tenths. This is 8 hundred thousandths. 3 thousandths is greater than 8 hundred thousandths. You see, the value of the digit here didn't matter, because when you take the place value, the 3 is in a position that has greater value than the 8 is. Just like up here, this one was in a lower position than this one. Strategy 2, bigger exponents make bigger numbers. Here's another one for you. A red blood cell has a diameter of 7.6 times 10 to the negative third millimeters. A granule or nerve cell has a diameter of 4 times 10 to the negative third millimeters. Use greater than, less than, or equal to compare the sizes, and how do you know? Tell you what, here's your red blood cell, there's its diameter, there's your granule, and there's its diameter. We're trying to figure out whether we should use a greater than, less than, or equal to compare these. We have two strategies already. The first says look at the front, because positive numbers will always be greater than negative numbers. Notice here they are both positive. That does not help. Rule number 2 says look at the exponents. Those numbers that have larger exponents are going to be larger numbers. That does not help here because these are both to the negative third power. So we're going to have to develop strategy number 3. Strategy number 3. To help us with that, I'm going to put these both into standard form. Notice that the negative 3 says move this decimal 1, 2, 3 places to the left. Same thing over here, move this decimal 1, 2, 3 places to the left. And look at what you end up with. This is 76 tenths, hundredths, thousandths. This is the 10,000ths place. So I have 76 10,000ths compared to tenths, hundredths, thousandths. This would be the 10,000ths place. It's 40 10,000ths. Notice that when I write them so they have the same number of decimal places, it's very easy for us to tell that 76 10,000ths is going to be greater than 40 10,000ths, or 4 thousandths. Greater than. That gives us rule number 3. If the exponents are the same, all we have to do is compare the factors, because regardless of what the decimal value is going to be, or the place value is going to be over here, if these are the same, the number that's larger in the front will always give you the larger value. Tell you what, try these. Notice once again they're both positive, so I can't use strategy 1. Once again, the exponents are the same, so I can't use strategy number 2. That means I need to look at strategy number 3, which is compare the factors. This is 8.15. This is 8.12. 8.12 is going to be less than or smaller than 8.15. Notice I did go ahead and put this into standard form so you could see it. Notice this is 8,120,000. This is 8,150,000. 150,000 is bigger than 120,000. So we have 3 strategies now for working with scientific notation. Strategy number 1, positive numbers are always greater than negative ones. Strategy number 2, the bigger the exponent is, the bigger the number will be. And strategy 3, when the exponents are the same, we just compare the factors. Now, this is not just a list of 3 strategies, but this is a list of 3 strategies in order of priority, meaning you always want to try strategy 1 first. If that does not help you, then move to strategy 2, and if that does not work, move to strategy 3. These are listed in priority. So a negative number being smaller than a positive one, or a positive number being larger than a negative one, is always going to take precedent over the other 2. So what I'm going to recommend that you do is pause the video, try these on your own as you go, and then restart in between each problem. Since you're watching this as a video and you have the opportunity to pause, I'm just going to go right on through these, assuming that you are doing that on your own. In this first example, strategy 1, positive numbers are greater than negative. These are both positive numbers. That does not help. Strategy number 2, bigger exponents make bigger numbers. These are both the same. That does not help. Strategy 3, when the exponents are the same, just compare the factors. So when I look at these, I see that I have 6 and 28 hundredths. Here I have 6 and, this is 80 hundredths, or 6 and 8 tenths. 6.28 is smaller than 6.80, therefore this is going to be less than. How'd you do? Try this one. I'm going to go ahead and hop right in. Strategy number 1, positive numbers are always greater than negative numbers. This one is positive. This one is negative. This is also a less than. I didn't even need to try strategy 2 or strategy 3. Love it when that happens. How about this one? Let's see. Positive numbers are always greater than negative ones. These are both positives. That does not apply. Strategy 2, the bigger the exponent, the bigger the number. Notice that 6 is bigger than 2. That means the one on the left is less than the one on the right. Now, I did want to throw in one more. This one's a little bit tricky, and I want to talk about it because strategy 1 says positive numbers are always greater than negative ones. Take a look right here. These are both negatives. We've not seen that happen yet, but it does eliminate strategy 1 as a possibility. Let's go on to strategy 2. The bigger exponents make bigger numbers. Notice that 10 to the 6th is bigger than 10 squared. So this is going to be a larger number than this is. However, if you remember from our integers unit, when we're talking about a number line, if I have a very large value in a negative direction, that's going to move farther and farther to the left of 0 on a number line. In other words, when I get larger values, but I put a negative in front of them, and it's farther to the left, the larger value is actually smaller than the bigger value. Does that make sense? That's just a little bit tricky. Let me put this into forms you might recognize. If this was just -4, and this was just -2, a 4 is a larger value than a 2, which means it's farther away from 0. But since we're moving in a negative direction, -4 is farther to the left, which means it has less value. You may want to pause and think about that for just a second. You may want to replay that and listen to it a couple times, because when both of our numbers are negative, that is really the trickiest part of what we have to do here. What we want to do is we want to think about the scientific notation itself first, and then try and realize what that negative sign does in terms of direction. All right, let's put all this together now. Suppose I gave you a list of numbers like the ones you see here on the left, and I ask you to put them in order from least to greatest. We're still going to follow the 3 strategies that I gave you in the previous slides when we do this, and we're going to use those in the same order exactly like we did before. Remember, strategy number 1 says that positive numbers are always greater than negative numbers. So what I'm going to do is I'm going to look at my list here, and I'm going to try to find those values or those numbers that are positive. Notice I have a -1.6 and a -6.2. Everything else is positive. The negative numbers are going to be first. Those are smaller. The positive numbers are going to be listed next. Those are larger or greater in value. Notice I'm not done with the problem yet. I've simply sorted my positives and negatives because I know that these two will come first, these four will come last. Let's move to strategy number 2. The bigger the exponent, the bigger the number. So when I look at my list now, already separated, I'm comparing exponents now. Notice 10 to the 5th is going to give me a bigger number than 10 to the 3rd. But because we're dealing with negative numbers, the larger the scientific notation number is, the lower the value will be. This is a very large number in a negative direction. This is a smaller number in a negative direction. Since this one is going to be closer to 0, it has a greater value than this one did. Whew, that's taken care of. Let's come down here. We said bigger exponents are bigger numbers, so the biggest one is going to be 10 to the 9th. The smallest one is going to be 10 to the 3rd. 10 to the 3rd. Notice you have two 10 to the 6ths in here. I'm going to list those together. And I'm going to put my 10 to the 9th last. Notice these two are now in order. This is now in the right spot. This is now in the right spot. The problem is these two scientific notation numbers that have the same exponent. To sort those, we have to go to strategy number 3. When the exponents are the same, just compare the factors. So when I look at these two right here, I can see that 8.79 is smaller than 9.2. So the final answer here is the values that I already know, and then the 8.79 is going to come first. There's your final answer. Now that is a very long, drawn-out process, isn't it? I would encourage you, at least starting out, to take the time to walk through all these steps, maybe even on paper. I certainly would not recommend that you spend forever rewriting your list 3 times trying to get it right, but it is certainly worth your time, at least mentally, to begin the sorting process the exact same way. Very, very important that you take your time with this. It is not quick and easy. I do want to point one thing out to you when you reach the end. Notice what your exponents are doing here on the right. Notice that you have your large exponents on a negative number making your smallest values. The exponents get bigger, or sorry, the exponents get smaller. Then when you hit the positive numbers, they start growing. This is a good way to check yourself. Your exponent should always look something like this. You should have big values going to small values with your negative numbers, and then small values going to big values with your positive numbers. Did you get that? I'm going to recommend that we try this one more time. Again, taking your time, pausing the video, trying it on your own, and then restarting the video to see if what you did matches what I have. Strategy 1, you want to separate your positives and negatives. Your negative values should come first because they are going to be smaller. Your positive values are second because they are larger. Now, these negative values are not necessarily in order yet, but we do know these 3 will be the first 3, these 3 will be the last 3. I'm then going to use strategy number 2. The bigger exponents make bigger numbers. Remember, when I'm dealing with negatives, the bigger the exponent is, the bigger this scientific notation number is, the farther below 0 it is. That means that since 10 to the 4th is my largest number, or the farthest move in the negative direction, it is going to be my smallest value. Going in order then, my next would be my -2, and my next would be my -5. Notice these exponents are starting big, and they're counting down. Let's take a look at our positives. I have a 2, a 2, and a 6. Those are already in exponent order, so I don't need to worry about sorting those. That brings me to my last step, because I still have 2 that have the same exponent. Last step says take these, leave them where they are, but then if the exponents are the same, compare the number in the front. I'm going to compare this 9.15 to the 4.3, and the 4.3 is smaller, so it should go first. Again, look at your exponents here. You're starting with big numbers, you're going to small numbers, then you're going small numbers up to big numbers. Hopefully this has been useful for you. I did try to break it down to some very specific steps that you can take. I know sometimes we as teachers have a tendency to gloss over and just say, hey, you should be able to look at this and realize it. But if you have specific strategies that work in every single type of problem, I think you're going to find this to be a whole lot easier. As always, I do appreciate you taking the time to join us here today. I would appreciate it if you'd smash that like button for me so that I know that this has been useful for you. Also, if you are following along with us, make sure you ring that bell to turn on your notifications so you receive all the new information coming from us here at Nunley Math. I do wish you all the very, very best. Take care of yourselves, all right? Bye-bye.